Hello, my name is Thorsten. I'm Product Manager for the tool family ASCMO, which is part of one of the 5 application fields of ETAS, Measurement Calibration Diagnostics. Today I would like to give you an overview about one of the tools in the ASCMO family, MOCA. So what is ASCMO? ASCMO is a tool family for data-based modeling and model-based calibration. It consists of 3 main tools. The first one is our classic product, ASCMO Static. It is a tool for data-based modeling of steady-state behaviors of technical systems. The next one is ASCMO Dynamic, same idea as ASCMO Static. It's a tool for data-based modeling of transient dynamic data. The third tool is now ASCMO-MOCA, what is a tool for efficient parameter optimization of physical-based models. This is the main topic of today's presentation. Beside these 3 tools, we have some additional functionalities. First one is a drive cycle manager, second one is a visualization topic, and the third one is a calibration data editor. All of these tools are part of the ASCMO family. So let's talk about use cases of MOCA. The first important use case is to have a physically based model serving as a virtual sensor on an ECU, such as an air charge model, torque model, emission model, temperature model. The second important use case is use such a physically based model as a blend model in an XIL environment. For example, as a battery model, a drivetrain model, air charge model, or others. Now let's see how this is realized in MOCA. First of all, you need to have a model. In this case, we have a very simplified torque model, 3 inputs, 1 output, and 4 internal parameters. The first step in MOCA is now to provide this model to the environment. That means you can write it down as a formula, you can provide it as a Simulink model, SCAD models, or others. The next step is provide measurement data, typically measured at the engine test bench or in a vehicle, providing data that stimulates the inputs of our model, here speed, air mass and ignition, and provides a measured output, in this case the torque. Now we can compare the calculation of our model, so our simulated torque, with the real measured torque for all combinations of the input parameters. You will see we'll have some deviations. And now the calibration or optimization task is change the parameters, the maps and curves in a way that you minimize the deviation between the measured and the predicted output. This is the task of MOCA. And now let's see how this is realized live in the tool. Here you can see the MOCA start screen, where you can load existing projects or completely start from scratch. This is what we will do later. You have also the chance to load an example project, where you can find here on the left side. Different types of models and examples are available. So as a function, or using a Simulink model, or an FMU, or all the others. But in our example now, we want to start from scratch. That's why we just click on Start MOCA. Now we see this main screen of MOCA. On the left side, you can see the different options that we have. We need to load data, we need to define models, we need to define functions, parameters, and the optimization. But let's start at the beginning with loading data. Here we can select what kind of data we want to load, steady-state data or dynamic transient data. In our case, we want to load steady-state data. So no time channel, no inner states, purely steady-state data. Just click on this button to load a measurement file. Select one of the files. In our case, we have an Excel file of measurement data coming from the engine testbed. Other options are CSV files or text files. But we select the Excel file, just open it, and you will see it here in the first screen. There is an Excel style. Here in the upper part, you see different columns with the measurement channels, speed, relative air mass, ignition, torque. And on the lower left side, you see the list of available channels. In this example, we now select all of these and define them to be imported. Now you see it on the right side. That's all. Simply press import. And now you see it here in the main screen. Again, we have all the information we need. We have the different columns for engine speed, relative air mass, ignition, and the measured torque. These are the available channels that we have in the project. On the right side, you can work on this data, activate, deactivate, change a weight, delete some, delete columns, or sort it or filter the data. This is the handling of the dataset. In addition to this, you can also for sure load additional datasets. We now have just one. You can define the weight for each dataset. And here in this pull-down menu, you would see the different datasets where I can select one of the datasets to be used. On the lower part, very important, you see a channel name mapping. Here you can see the names as they are loaded from the measurement file. They can be different in the different measurement files coming from different regions, from different test benches. All of them will be mapped to MOCA internal names, what you can find on the left side. So here you see the names that are used in the project of MOCA. Speed, rate of air mass, ignition, torque, and so on. You could change the name if you like. For example, name it engine speed, but for this example, just keep it as it is. These names will be used in the project of MOCA, independent from the names that exist in the measurement channels. This is the first part of the definition. We have loaded measurement data. The next step is now to load parameters from, for example, a DCM file. So click on this parameter section. You can see on the left side, we have a similar concept as in Inca with a work in a reference page. You will see this later in the project, how it is used. You could create a new parameter completely from scratch by just press the button create, or in our case, we want to load a DCM file. That's why we press this button, choose our DCM file. Beside DCM, we have a lot of additional formats such as CDFX file or CSV or others. In our case, we now load DCM file, simply press the open button. Then you get the possibility to select which channels you want to import. If you don't want to have all of them, you could select or deselect some of them, or just choose all and then press import. Now we have loaded successfully a DCM file. The parameters are in our MOCA project. You can see we have maps and curves and other parameters. They are available as parameter within MOCA. They are visualized in a graphical representation, so this calibration map, and also in a table view. You can change the parameter by simply using the mouse, change this parameter, or also change the numeric value here in the table. So this is how you can influence the behavior of the parameter. Now we have successfully loaded measurement data. We have loaded a calibration data set. So the next step is define our model. Load our model to the project. For this, we could now go directly to the model section, where you can add additional models such as FMUs, Simulink models, or also TSIM models, or all the others. But in our example case, we don't want to use this model import. We want to write down the functionality directly as a formula. That's why here on the left side, we now click on the button Function. In the Function section, we can now define how our function works. For this, we have the possibility to enter different lines with the expressions that represents the behavior. So the first one here, you open the formula editor. On the left side, you see our available measurement channels, speed, rate of air mass, ignition, and so on. In the middle part, you see the parameters that we've just loaded from DCM file. On the right side, you will see later we have different nodes, so the intermediate calculations that we have created earlier. As a first formula that we want to enter is now interpolating a calibration map, as it is one of the first parameters that we have in our formula structure. For this, just double-click the parameter. You can see we need two input parameters for this map opt torque. The first one is engine speed, double-click on this. The second one is relative air mass, double-click on this. And you can define a name. Let's choose torque opt, because this is the result, the optimal torque. Press OK, and you can see it. Now we have the formula here in our view. Torque opt is the interpolation of a calibration map in red with two inputs, speed and relative air mass. The green entries are coming from the measurement data, the red one from the parameters. This was the first entry. And the next section is now just add the next calibration map, double click again. Again, we have two inputs, speed and relative air mass. Now let's define a name. In this case is the optimal ignition, that's why ignition opt. And we have the second entry. That's exactly the way how these entries are done. Now let's continue with another formula. The next calculation we need, if you have a look in our formula structure, we have the optimal ignition minus our measured ignition, and this results in our delta spark value. So this is not an interpolation of a calibration map, it's simply a calculation with existing channels. The next entry that we need to do is using our curve, a calibration curve, not a calibration map. For this, we click again on New, then double click on Add a delta spark. This curve has now an input, but in this case not an input from the measurement channel, but an input from one of the calculations that we have done earlier, delta spark. Double click on this, define a name, it's ETAS spark, and just press OK. So this is exactly the process that we need to go. We have a curve with an internal value, delta spark, that has calculated in one step earlier. And now we can continue with the rest of the calculations. The next calculation we need to do is a calculation, torque opt, multiplied with the ETAS spark, and this will result in a value, not really a clever name, just call it product. And press OK. So the next calculation we need to do is again a calibration map. So the map opt, the map track torque, again with two inputs, speed and relative air mass, and the name is track torque. Press OK. And now finally the last entry we need to do is the final calculation. This is the product we have just calculated minus the track torque. Double click on track torque, define a name. Let's call it our torque predicted, because this is predicted by the model structure we have defined. And press OK. That's all. Now we have in 7 lines of code, we have defined the logic of our simplified torque model. So we have measurement data, we have parameters, and we have the function defined. The next step is now start performing optimizations. Click on optimization, and here you see all your parameters again. Just rearrange a bit, that's easier to see. And a list with checkboxes, what defines which parameter should be optimized, which not. So if you deactivate it, it will not be changed by the optimizer. Then we have a smoothness factor that defines how smooth the calibration map should be, and we have lower and upper limits to define the range in what the optimizer is allowed to change the value. This is something that is a pre-knowledge, what can be included here. In our case, we want to go from 0 to 500. For the second parameter from 0 to 600, and for this parameter from 0 to 100. So now we have defined the boundary conditions of the parameters for performing the optimization. The next step is to define our optimization criteria. This can be found here on the left side. The first step is to select the two channels that we want to compare. This one is now the torque predict. This is the result of our formula that we have entered. And we want to compare this with the torque measured. This is the result from the measurement file. And this finally leads to an RMSE of 13.4 Nm, what is pretty bad, but we have not optimized so far. So this is the calculation done for 2,800 measurement points with the given parameter set, with the given function structure that leads to 13.4 Nm RMSE. Next step would now be start the optimization to make this calibration better. Before we start the optimization, we want to analyze our data. And for this, we have the possibility in our analysis menu to show the absolute error analysis figures. If you click on this, some figures will pop up and you see different plots. The first important one on the upper left side is the distribution of our errors. We expect to have it normally distributed. In this case, as you can see, it's not. But we have not optimized the parameters, so that's not unexpected. You can also see measured versus predicted on the right side and other plots for the errors and the problems over the outputs and the inputs. But let's close this. So now we are ready to optimize. For this, we simply click on the button Optimize. Just wait in this case for less than 1 second and get our first result. You can see the RMSE went down to 1.3 Nm, what is pretty good for the first run of optimization. The optimizer has now changed all parameters of all my calibration maps and curves in a way to minimize the RMSE. That's exactly the task of the optimizer, to minimize the RMSE. That's what we have defined. We could now export the results directly, for example, to a DCM file, or also other formats such as CSV or CDFX. Just select the format, choose your name, My Results, and save it. Not necessary here for the demo, but this is the way how you export the results as a final step. So this was now the brief overview about the main steps you need to go for optimizing such a physical-based model in MOCA. Using the formula approach, write it down as a formula, very fast, very efficient to optimize. To check the quality of our result, we can again go back to our analysis menu and start the absolute error analysis again as we did it before. And now you see, it looks much nicer. We have a nice normally distributed error bars. We have a very smooth measured versus predicted plot. And you can see we have 2 measurement points already marked with a red circle. These are possibly outliers, so measurement points that does not fit to the rest of the data. They are suspicious. That's why you can mark them if you like, you could remove them or just keep it as it is. So this was the final analysis of the data in one of our standard plots. In the next step, I would like to show you how to improve the optimization result even more. Right now we have an RMSE of 1.3. Let's see if we can make it even better. One possible option is to change the number of grid nodes of the calibration maps. That means the optimizer has more chance to vary the shape of the calibration map to improve the quality of the RMSE. And how to do this? Simply click on Edit Parameter. Then you can choose the number of grid nodes for each direction. Start with the X-axis. Now we have 6. Change this to, for example, to 10. Press OK. Do the same for the Y parameter. Here we have 5. Change this also to maybe 10. Press OK. And again OK. And now all calibration maps with the same group axis have been changed to a 10 to 10 calibration map. And now let's see what happens. We have an RMSE of 1.3. Let's press Optimize. So now we have a remaining RMSE of 0.9 Nm. What is a dramatic improvement against the 1.3 Nm that we had before. So by changing the number of grid nodes to a new number, we have the chance that the optimizer can find better results. That's the final result after this run of optimization. Also this result for sure can now be exported to DCM or other formats. Another option to improve the quality of the optimization is using the sequence. And sequence means you have the chance to influence the behavior of the optimization routine step by step. How to do this? Let's click on the tab Sequence and you can define different commands. Let's start with a simple example. Select a parameter, for example, just select the first parameter and enable only the first parameter. The other parameters will not be used for the optimization and for all further steps. So, second step could then be select dataset or data. In this case, just a simple example, I want to use only my measurement data where engine speed is below 3000 RPM. And in the next command, I can now start the optimizer with default settings. No need to change. So this would be the first run. Then we can continue. So select the 2 parameters that should now be allowed to be optimized. Enable them with just a 1. And the next option that we can do in this command list is reduce the grid. So reduce the number of grid nodes that we have in all calibration maps with a reduction factor of 2. And finally, start again the optimization with maybe a bigger number of optimization runs or iterations with 50. So this could be a very simple sequence that can be used. And to activate the sequence, you can just check this checkbox, use sequence, and then start the optimization. MOCA will now use the command list that you have defined in the sequencing. This is a very nice way to influence the way the optimization is done in MOCA to get better results, easier results, clearer results. So this is the standard way of doing optimization in MOCA with some of the different options. Now I can show you the same use case or the same task using Simulink model instead of our formula that we have created. Here I have already started the same project using our Simulink model. In the data section you see the same as before, but in the model section you now see we have selected a Simulink model including a preload script, so everything what should be executed before we run the model. We need to do the parameter mapping, the input mapping and the output mapping, that MOCA knows how to handle the Simulink project. If you press the button validate, it will now start Simulink in background and execute the model with the given dataset, saying, hey, validation was successful, so I do have access to my Simulink model. This is now linked to MOCA. In the function section, it's just one simple call, calling the Simulink model and delivering 3 inputs. Parameters are the same as before. We have our given calibration dataset. And in the optimization section, it looks also very similar. The only difference is that in the optimization criteria, we are not using our calculation from the formula, but our Simulink model. You see the same RMSE, 13.24 in this case, with the Simulink model. You could now start performing the optimization. Simply press on the optimize button, and instead of this internal formula, the Simulink model will now be used. To show you how this interaction is done between MOCA and Simulink, if I now modify some of my parameters here in MOCA, you see directly live in Simulink the change of the parameters. So both tools are now linked to each other, and if I change something in MOCA, it will also be changed live in Simulink, and that's exactly what later the optimizer will do. Let's summarize. ETAS ASCMO-MOCA enables the automatic optimization of all model parameters at once, while minimizing the deviation between the measured and the model outputs. The needed models can be provided in standard formats, such as formula-based, Simulink, SCAD, FMU and others. With its intuitive user interface, with logical steps, it allows a smooth and easy use even for less experienced users. Please contact us if there are any questions left or to discuss the next steps. Thank you for your attention. See you next time.